Hello and welcome to this week's What Were They Thinking? Amongst the news items we have for you this week, there is the ever-growing issue of COVID-19 amongst white-tailed deer, and the apparent evolution that it's experiencing. Amplifying RNA vaccines that could be the next development. A drug development in mice that may theoretically, possibly, sometime in the distant future, help with obesity. A relatively common drug may help considerably with Alzheimer's disease, although it's not the only example this week. A novel antibiotic, which could at least somewhat mitigate the issue of antibiotic resistance. A hybrid neuron involved in brain function. The bizarre nature of, genetics and its relationship to math. Leftover coffee grounds could be used for a surprising number of things. The bizarre observation of a car modified to accommodate a bull. And we have the surprising performance of ChatGPT. The timestamps for these and other news items can be found in the description box below. Let's start with the somewhat predictable outcome. When you infect an animal with COVID-19, or for that matter, any virus, there is a decent chance it will begin to mutate. This is exactly what we observe with, COVID-19 and the other coronaviruses in the family. Of course, not just coronaviruses. For instance, we do have influenza in birds. Generally it goes bird flu, swine flu, human flu. But what's important here are the coronavirus family viruses, and much like MERS, SARS, and most recently COVID-19, they tend to find a niche in the environment where they take up residence, and that residence is generally an animal, and it acts as a reservoir. For COVID-19 at the moment, it's white-tailed deer, or specifically in America, it's white-tailed deer. For places like China and other parts of Asia, it's going to be bats and pangolins. But the white-tailed deer thing here is important, and it's something we predicted long ago. The issue that once it gets into this species and it becomes established, white-tailed deer are going to act as a reservoir, and unfortunately, as we did not predict accurately, it's going to begin mutating, and mutating rapidly, far more so than you would have expected. That's already a concern, and the rapid mutation of COVID-19 in deer is likely to lead to a new variant of concern before long, and even if it doesn't come before long, it is inevitable. The bigger issue, and this is something that is noteworthy, it's apparently reinfecting humans more readily than other examples have. In fact, we don't really have other, known examples of animals infecting humans. The origin is assumed, and for good reason, but since then, we know nothing about a species such as cats, dogs, or similar infecting a human once the human has infected that animal. However, that is not the case with these deer. They are reinfecting humans. The final disconcerting element to this is that nothing is isolated. That is to say, this is not a small number of deer, but at least a quarter of the population that was sampled, which does indicate a significant spillover into their population and then back to humans once more. In rather more entertaining news, at least, related to COVID-19, the most recent idiotic conspiracy theory has been announced. And it's a doozy. As you can see, the Marburg virus has apparently been put into the vaccines people received, and that when you get 18 gigahertz pulses from 5G towers, suddenly we're all going to get the Marburg virus activated, and just no. 5G by itself tells you what the frequency is. It's 5 gigahertz. How you get 18 gigahertz from a 5 gigahertz tower just shows how stupid some people can be, let alone the ability to pack the Marburg virus into the human body via a vaccine and not have it already taking action. It's just no. This just seems to be a variation on older anti-vax conspiracy theories where supposedly vaccines contained AIDS, which, as is quite clear given the fact that AIDS is relatively isolated now, is not true. Nonetheless, apparently we should be waiting for October 2023 to laugh at these idiots for, well, being idiots. Next we have news that builds on it with the, role of RNA vaccines. And in this case, the idea that you could, in theory, be able to use messenger RNA and get it to amplify the immune response. And by self-amplifying it, it's able to get a more pronounced immune response and therefore better immunity. This is otherwise known as a self-replicating RNA vaccine. Your typical mRNA vaccines have what is arguably one fundamental limitation. That is, the mRNA will eventually expire. And by expire, we mean it's either going to be broken down by the body, or alternatively, a translation is going to occur so often that you effectively wear out the mRNA. And that is a gross oversimplification, but you get the general idea. With a self-amplifying RNA, you're able to effectively mitigate both of these issues to some degree. The way it works is that the vaccine itself includes an RNA-dependent RNA polymerase. This is basically a molecule that will copy the RNA once it is there, and this allows for a much smaller dose of RNA to be used, or messenger RNA more accurately, and this can then be copied in the human body. This means you get a small dose, but it lasts for longer, and obviously not as much of the vaccine is required. This allows you to effectively save cost in some respects, but also to have a better immunological response. Of course, not everybody has taken this so very well. Again, anti-vaxxers, conspiracy theories, and other special needs individuals have all jumped on this and jumped to the erroneous conclusion that somehow or other having the ability to replicate the RNA that is in the body is somehow going to lead to other issues. Of course, the how, what, where, and why have never really been explained, other than to say that, well, because you can copy the RNA, it must therefore be dangerous. No, this is not the case. You could photocopy the instructions for making a bomb. That doesn't mean that the instructions are any more dangerous than the original. On to further news, and again, slightly more promising, but to be clear about it, you should be taking this with a lot of salt. The idea is that we can hopefully address both cardiovascular disease and cancer using a single drug, ironically. We say ironically given that, well, neither cardiovascular disease nor cancer are actually single diseases. Cancer is basically any and every tissue in your body, and arguably even then there are some subvariants. That is depending on what kind of mutation has led to the rise in cancer. Cardiovascular disease, however, is significantly more narrow by comparison, as it is, well, the heart and arterial system that's affected. This leads to, the treatment in question, and it all relates to the role of immune cells, and what those immune cells do, both in the case of cardiovascular disease, but also cancer. In theory, for both diseases, you have to look at the macrophages. Macrophages have a role to play in either cleaning up debris, or, in the case of cancer, attacking the tumor itself. So, if you can target the macrophage and get it to do the job specifically it needs to do for either disease, you're able to drastically improve clinical outcomes. This is all well and good, except how do you get to that end result? You look at the sodium glucose cotransporter 2 inhibitors. Now, these are already a target, but they're a target for something used for diabetes, which kind of makes sense. I mean, if you're going to be interfering with a glucose transporter, either increasing its activity in the case of diabetes, or preventing it in the case of, say, tumor cells, you get benefits. But then, how does cardiovascular disease and the macrophage fit into this in particular? That's where a novel treatment using nanotubes comes into play. Those macrophages normally home in on damage, or, in the case of a tumor, errant cells that have mutated. By getting those macrophages to deliver these nanotubes to tumors or cancerous cells, you're able to basically destroy those cells because the nanotubes get injected into the tumor cells and destroy them from the inside out. Those same nanotubes can also be used in other ways. They are kind of like a delivery vehicle, and it allows you to, make them active against things like lipids in the role of plaques. That is one of the major issues with cardiovascular disease. Atherosclerosis, or plaques in your artery, are pretty much a big risk factor that comes from that. Once they break free, they float off somewhere else, block the flow of blood, and it leads to, ischemia. Ischemia eventually leads to tissue death, and tissue death leads to, generally speaking, very nasty outcomes. Of course, the Trojan horse approach could be interesting in knowing, Trojan horse is the name itself tells you everything. It's a trick, but the body isn't very smart at times, and whether or not the idiotic body can manage to differentiate between when it should and shouldn't be using it is going to be kind of important. Going on to further news that is very, early on in development, we have a phase 1 clinical trial that has been effective in mice, but how well that will translate to humans in the long term is, relatively unknown, given that this is a phase 1 clinical trial. The idea behind this research is that they're going to target a receptor called GABRA5. It's a GABA receptor, as the name would indicate. And GABA receptors are a receptor for neurotransmitters. What they were hoping to do was that by targeting this, they're able to interfere with the way the neurons in the body indicate whether or not you are hungry, or more accurately, whether or not your body should be metabolically active, so at a cellular level, are they hungry? When you stimulate this, you're able to get the body to increase the thermogenesis, that is the production of heat, and this, in order for that to happen, requires metabolism. Therefore, it artificially boosts your metabolism. As you increase thermogenesis and the metabolism required for that, you decrease the available energy in the body. And that's because you are literally burning it for heat. Since the body only has so much energy available at any given time, it now has to start drawing on your fat stores. And as it draws on those fat stores, you lose weight, unsurprisingly. Again, this is a very early work. Just keep that in mind. And it has primarily been proofed in an animal model. There are some issues around the animal model, primarily the particular, breed of mouse that was used. It appears to be Black 56, which is fine. They're a fairly common cardiovascular disease and metabolic research-focused variety of mouse. It's just a question of how well the particularly genetically modified mouse works. Further building on the drug development pathway, but this time not a novel drug so much. It's rather a novel application of an existing drug, and specifically, a drug intended for multiple sclerosis may have applications for Alzheimer's. As already said, take this with a lot of salt, as it is very preliminary, and preliminary research tends to be overhyped and often fails to live up to expectations. This is why at least having the pre-approved drug for something else makes things more not necessarily optimistic or likely, but certainly much easier to see playing out. Generally speaking, although already approved drugs being approved for a novel application will take time, it takes a far less time than trying to get a completely new drug approved. So rather than it taking 20 years, it may only take 5 or 10 years. And now for the, actual activity of it. The medication is an oral medication used for multiple sclerosis, and it's pretty much intended to, try and put the lid on immunological activity in the brain. Basically, reduce the amount of inflammation. By reducing the amount of inflammation and overactive immune cells as a result, you generally see fewer symptoms. And this is also the underlying theory for Alzheimer's. So by taking ponesimod, which is the drug, You can give it to someone with Alzheimer's and block the immune activity in the brain, and thereby, theoretically, help with Alzheimer's. But understand, this is all theoretical, and theory's translation to fact is, well, questionable the best of times. This research at least has a better grounding than other translational topics from this week have. That is because we actually know a fair degree about what's happening. In the simplest terms, inflammation in the brain leads to the neurons getting damaged, effectively unintentionally, but nonetheless it occurs, and as the damage slowly builds up, you get the, degradation of neurological function. By putting a sort of limit on how much inflammation and neurological activity can occur in the brain, you can drastically slow down the degree at which the degradation occurs. It's kind of like trying to slow down the flow of water over a dish you're trying to wash. You will still get there eventually, but you can only wash off so much dirt at one time. Of course, this will come with some notable drawbacks. The most obvious will be that whatever damage has happened already will be there and will stay there. There's no way to reverse the damage. The second is that you are interfering with the immune system. And anytime you begin to interfere with the immune system, you open the door to, immune problems. Whether that is autoimmune issues that it causes, or more likely, by suppressing the immune system, you're opening up the individuals to, infection and other pathogens that you really don't want to have them being infected by, since you've just kneecapped their immune system. In further Alzheimer's news, there is at least, some more immediate but also similar news relating to the use of sleeping medication and dealing with the buildup of the proteins associated with Alzheimer's disease, those being the tau bundles. The American research found that Silvexerant, a treatment for insomnia, theoretically improved the tau protein and amyloid beta protein buildup in Alzheimer's disease. Unlike the previous research, which is both very preliminary and very vague at this stage, we have a slightly more substantial study, but also one that is incredibly small. So we're talking a tiny cohort, which means the results may or may not translate in any way, shape, or form. It's more a proof of concept than an actual result. However, based on what they have published, the drug did appear to help considerably. Well, considerably given that there were 38 individuals who took it over just 2 nights, so the results don't really speak to anything substantial. Further, the individuals were aged between 45 and 65 years of age, which again is a very narrow selection of participants, and again speaks to issues around the inferability of the results beyond the study in question. The amyloid beta and tau protein concentrations did reduce by up to 20%, so it's a substantial decrease as mentioned, but a substantial decrease for a very narrowly tailored study. Sadly, the medication will do absolutely nothing for the tau itself, as nobody likes tau players. Staying in the brain and focusing on neurology still, but this time neurology and oncology, we have a possible treatment for an aggressive kind of brain tumor. Brain tumors are, generally quite nasty, but particularly this kind, as it's not only very central to where the brain is, therefore hard to get to for surgical treatment, if not arguably impossible without significant damage on the way, but it also generally occurs in children. So, yeah. Because there's no treatment, really, other than, chemotherapy, and, that's not going to do a great deal given the location of the tumor, and you can't really do surgery for it, it's pretty much a death sentence. This is where drug prospecting comes into play, and it's a drug called ONC201. It's already being chased for other kinds of tumors or cancer, but in this case, it's found to be particularly useful against this kind of cancer, or this kind of tumor more accurately. Again, however, bearing in mind that it's a small study, it's very early, and, well, there are all kinds of other issues with this, and, well, the children. The study involved a cohort of children and adolescents, roughly 30, although there was another complementary study that had 40 adults. The treatment was given to them and they were followed for 22 months on average. About a third of the patients survived for 2 years. Those who didn't have treatment survived somewhere between 11 and 15 months, so there was a notable improvement being an operative word, but given that these kids were basically going to die regardless, given the nature of the cancer, it is, well, arguably better than nothing. One of the major reasons why a lot of, well, chemotherapy and similar anti-cancer drugs don't really work for, well, neurological cancers, and particularly this kind deep within the brain, is the blood-brain barrier. Nominally, the blood-brain barrier is intended to, well, keep things like pathogens outside of the brain and ensure that that squishy thing inside your skull, which is essential for life, remains protected and functional. The downside to that is that if something does go wrong internally, it's a hell of a lot harder to do anything about it. As a result, the drugs that are used now simply can't get to it unless given at high doses that, well, create all kinds of other issues, and once you start getting to those kinds of doses, especially with children, you're likely to experience a lot of off-target effects. Whether it is something, well, in this case, as benign as sterilization, or as serious as basically destroying other parts of their body in the process, and then causing them to die. You can see why this is generally going to be very hard to treat. This compound can get through the blood-brain barrier, or at least significantly more so than the currently available offerings do. Moving on to other novel drug discoveries this week, and we have a novel antibiotic resistance mechanism. Well, sort of. The issue here is that it's a soil-borne bacterium from North Carolina, so we don't know if this is a novel bacterium or if it's just incredibly inbred. The important discovery out of this bacterium is a substance called clovibactin. Clovibactin is the novel antibiotic that effectively doesn't fit into any of the presently known antibiotic resistance pathways, which is helpful as there is a arguable case that with the growing number of resistances and the growing number of bacterium that have resistance, we need these, more so than ever. Although, arguably, there's a less urgency on antibiotics for most instances than there are, say, antifungals. The advantage of clovibactin over the existing structures we have is that because it doesn't fit into the existing framework of antibiotics that we use, it could theoretically completely sidestep the issue of any resistances that exist at present. That's because we don't have anything that would have selected bacterium to be resistant to it and thereby, well, basically give us a completely new way of attacking them. Although, again, a lot of, let's say, skepticism should be used as, well, beyond the obvious issue of it's very early in the stages of development, it could also take 10 to 20 years before we see it being used. The reason why we have this completely novel pathway or avenue of attack is that this particular bacterium wasn't able to be cultured before. It was one of those bacteria that just, no matter what you seem to do, it would not cooperate. As a result, having now been able to culture it, we can see what it's doing and, well, eventually new things emerge, including new antibiotics. As far as the mechanism goes, it's relatively simple but also complex. In short, and this is the very abbreviated version, the fibrils that the bacterium put on its membrane are able to bind to a phosphate molecule. And because phosphate molecules don't change, after all, phosphate is an element and effectively the simplest of structures you can target, it's able to always be able to hit that. It doesn't matter what resistances you develop, you will always have phosphate as a bacterium. Therefore, by targeting this and binding to it, and then, let's say, flagging the bacterium for the immune system, the antibiotic cannot be avoided, cannot be resisted, cannot have anything done about it. It will always work. But also, phosphates aren't just limited to bacterial membranes. For example, just about all, cellular, and by that we mean eukaryotic, cells have a bilipid phosphate layer. That is, 2 phosphates, one on the top, one on the bottom, and 2 tails that are lipids in between them. That means even our own cells would theoretically be targeted by this. It is worth noting that there have been what you could call clinical tests of this, although it's more accurate to say that they've run it against a battery of medication-resistant bacterium, including medication-resistant Staph aureus. You may also know this as MRSA or golden staph. Next we have a interesting, for lack of a better word, juncture between physics and biology, and that is Maxwell's demon. Maxwell's demon may have been solved by the cellular system, which is likely to annoy any number of physicists who claim that their science is more pure. Yeah. The short answer is Maxwell's demon is more of a thought experiment. The underlying theory to this is that if you had a demon that required no energy itself to be able to control a given gate, and that each side of this gate was a cool-sided gas and a hot-sided gas, you would be able to effectively create permanent and ongoing energy. This would be because the demon could control the movement of molecules and ensure that the laws of thermodynamics that basically say a hot gas would go to cold gas and eventually equal out didn't apply. Although this is a gross oversimplification. The way cells use this is, in a way, very similar. By using very specialized transporters across just about all eukaryotic cells, although even prokaryotic to some extent, they're able to do something, very similar, but not necessarily the same, although this is coming from a Swiss institute, so take what the École Polytechnique Fédérale de la Soine has to say with some salt, or given that this is Swiss, shall we say cheese. In practice, what we observe in biology is that by having a membrane and transporters that control the movement of molecules across it, we're able to ensure that the energy is always going to be in flux. That means you don't get any kind of, for lack of a better word, equilibrium reached. That's mostly because if you had an equilibrium reached within cells, there's a good chance the cells would lyse as water rushed in to try and get to an equilibrium with what's outside the cell. This is generally not good for life, so this is why you have arguably, defiance of the laws of thermodynamics. Shifting back to neurology, but this time focusing solely on cells rather than pathologies and neurology, we have arguably a new kind of brain cell. Understand that this is both very new and somewhat controversial. The new cell is supposed to be a kind of astrocyte, and astrocytes are cells, let's say, that play a role in holding your brain together, or at least all the neurons that make it up. One astrocyte is going to wrap around several neurons and create a sort of nexus and keep them all in position. They're meant to be mostly passive, that is, they're there to provide structure and support, but not really as much in the way of function, though they do have some roles to play in that respect. The fact that astrocytes not only sit in the brain, but also have a very close relationship to neurons, means there's been a lot of interest in them, and this interest is now being exacerbated by research indicating that not only do they support neurons, but that they can release glutamate. Now, glutamate is used for all kinds of things, but normally neurons would hold on to it themselves. Now, this brings up the question of what if the neurons are, say, incredibly active, or you have a pathology that prevents you from having neurons reabsorb the glutamate that is released? Well, if you have these astrocytes around and they act as a backup store of glutamate, they could theoretically be supporting them. The other option, and this is more along the lines of what's being proposed, they may act as a sort of backup neuron where they can release the glutamate by being stimulated by other neurons, and this in turn would, well, allow the neuron that wasn't working as intended to work. However, they were only found in very discrete parts of the brain, mostly in the hippocampus, so this is again very preliminary, very rudimentary, and we're not really sure how accurate, true, or inferable it is beyond the nature of what's been found. And most importantly, because, well, it's mouse-based research. Humans are, well, not very much like mice, for those who need that to be said. If we are going to go on to, let's say, complex research, the next bit of news might be helpful, although it raises all kinds of ethical and moral issues. It's the development of a human embryo from stem cells that is completely developed at 2 weeks. Yeah. This is going to be a massive minefield. So let's wander in aimlessly and see how many we can set off. Most stem cell research is already considered at least somewhat controversial, mostly owing to the historical aspect. That is, the stem cells initially were from either newborn infants or, in some instances, aborted fetuses, although that was incredibly rare by comparison. The movement away from the fetal stem cells to embryonic umbilical cord stem cells was more common. And then eventually we figured out we don't even need to do that. There are ways to make our own, and most recently that's been the go-to option. This is now arguably a massive step backwards, as we've now gone to developing human embryos from those stem cells cultured from, well, what could have previously been, say, tumor cell lines, skin cells. There are all kinds of ways you can get them now. You don't need to use anything from an embryo. And now we're back to making embryos. The model as it's developed is basically cut off at 14 days or 2 weeks, as that is considered the, let's say, absolute limit of embryonic research. And that's the issue here. Partly the ethical challenges that occur after that, but also for the purposes of most research looking at this, which is fertility-based, the 14 days is the end of what you need to look into. And that's because most birth defects occur sort of within this time frame to some extent, but in terms of fertility research, well, to be quite blunt about it, if the pregnancy is going to succeed or fail, a lot of the time, it will be in this window. So having 14 days to be able to figure out what's going on is generally enough. This is not to say that there aren't plenty of other things that occur after this period. For example, there's the whole, well, let's say travesty around thalidomide and the fact that the effects of that really only occurred later on in uterine development, particularly around long bones. But for the purposes of fertility and similar, this is why this research is useful, that again it raises a lot of issues around the ethics and morality of it. From a, let's say, a purely academic point of view, it does yield some incredible insights. One of the more noteworthy is that despite the fact that the embryo is completely synthetically stimulated, let's say, it's able to differentiate and self-organize with zero input from outside. This means that we can study how cells differentiate, which is a huge boon, but also how they self-organize, which could be particularly important if we're looking at, well, developmental disorders in particular. For example, why certain neuronal or eventually neuronal cells don't develop where and how they should, how you get certain tissues showing up where they shouldn't, and so on. Going back to, more controversial, let's say, if physicists think that they are the most pure science, then mathematicians think that they are not just the most pure science, but they are the most pure of all, barring theoretical mathematicians who are a creature all their own. In terms of what mathematicians have to do with biology, however, is that they're arguing that pure math is written into genetics, and particularly evolution itself, and how that selects for certain genes. This leads us to number theory, or your four basic functions: addition, subtraction, multiplication, and division. The number theories as they are, then how do they work exactly, and how do they work more importantly in relation to the genome? Well, the mathematicians think that it's the genetic errors that get into, any genome, let alone that of humans, over time, and how these in turn then push evolution in a particular way. The mathematicians did the most exciting of all research to, demonstrate this, and they looked at the maximum possible number of basically mutations that can occur with the phenotype, that is the particular kind of a gene and the way that gene is expressed, and whether or not that is what we actually observe in, real-world examples. What they found was that between their mathematical theoretical upper limit and the real-world upper limit, the two dovetailed fairly nicely. That is, effectively, life pushes the number of mutations as far as it possibly can, while still keeping the phenotype within, its phenotype, and still manages to succeed. That is, life effectively pushes for the widest possible diversity of, basic genes, and then selects from these. What surprised the mathematicians wasn't that life gets to the maximum number of theoretical, let's say, options, but the frequency and the fact that it seems to be applicable to just about all of the genes or phenotypes that they were looking at, although not everyone. That's where mathematicians and biologists somewhat diverge. In further news, we have a sort of experiment, although experiment is being rather liberal with it. The idea was that doctors would prescribe, and again being rather liberal with that term, fruit and vegetables 2000s, and then they would figure out what was going on with blood sugar levels, blood pressure, and weight. Yeah. This is basically telling people to eat well and be on a diet. The difference in this from our rather glib description so far is that this is an actual, widespread, somewhat widespread, study in that they've actually established clinical programs that give out the free food, and in some instances for a year or more. This is across the USA as well, so to be quite blunt, the USA is well known for its plus size, super size, and every other size meal, which more often than not is not healthy. The study itself that we're referring to in particular took 22 of these locations that had what they call a produce prescription, which, and it involved roughly 4,000 individuals, so we're talking a fairly widespread study with a modest participant pool, although 4,000 isn't exactly great. The results were, unsurprising, given that, food security was a part of what they were trying to address, but more importantly, from a clinical point of view, you had things like glycated hemoglobin, which is an indication of uncontrolled blood sugar levels, blood pressure, and BMI all improved considerably. Next we have use for, beans from coffee that are left over after they've been used. For most people, this is just a generic waste product. It's going to be thrown in the bin and sent off somewhere to be, ideally buried, but more likely burnt in some cases. This leaves a great deal of waste, especially for commercial businesses that operate making coffee. And this contributes to the significant amount of, let's say, organic waste that adds up over time. Organic in that it is derived from plants and similar. This is where research using coffee grounds in particular could be useful, and understand we say could, as with much other research it is both early and arguably it is overly optimistic. We say that as, what the researchers want to do is heat the coffee grounds to over 350 degrees Celsius or 650 or so freedom units, and in doing so they're basically going to bake it. And as they bake it, they break down some of the organic molecules and create something very similar to charcoal. It's not quite the same, but it's close enough for most purposes. They're then able to add this to things like concrete, and theoretically that then is useful for replacing things like, say, sand. What's important with this is not so much the source, let's say, that being coffee grounds, as arguably you could use any organic matter to do this. It is literally just making a kind of charcoal. Why you can't use coffee grounds in particular as is, and why they need to undergo this process, is that they do contain chemicals that, as the coffee grounds break down over time and various other interactions in the concrete, they actually weaken it. So it has to have this process done. Otherwise it becomes, a hazard rather than a benefit. Going to other environmental news, but looking at animals instead, and the surprising observation of a shark that can live for centuries. Yeah, these are probably both the happiest and saddest sharks in the world. The study looking at the Greenland shark found that they were able to observe one catching, fish off the coast of the Caribbean. A note, it's called a Greenland shark. Greenland is in the northern hemisphere and quite north, and not very aptly named given it seems to be covered in snow and ice most of the year. Yet it was observed in the Caribbean Sea. Yeah. It is worth noting that one of the reasons why they live as long as they do is that these sharks basically live an incredibly slow life. They're not very active, and they don't have sex until they hit 100. But at the same time, that's basically around the equivalent of somewhere along the lines of 18 or so for a human, given they can live up to 500 years. In further bizarre animal news, we have something out of Nebraska, and the unusual call police received for a vehicle that appeared to be modified in an odd way. It was modified to allow an individual to transport their bull in the front passenger seat. Yeah. The vehicle has pretty much been jerry-rigged to have half of the otherwise normally closed-in cabin boxed up enough that they can transport a rather massive bull for showing in various ways and times. Although it's a little morbid that they would put a pair of bull horns on the front of this vehicle while transporting a bull in it. Now that you may at least be somewhat more relaxed after that levity, let's go to archaeology and Israeli finds of, weapons from the Roman era that are sharp, and not just sharp, but pretty much as sharp as they were when they were hidden away, and that was somewhere around 1,900 years ago. But what makes the find, exciting is, several-fold, but most importantly is that these aren't Roman ruins that they're being excavated from. Rather, it's a small cave near the Dead Sea, which, along with other evidence, indicates that it was basically a rebel stockpile of weapons. If they had been found with these weapons, the Romans would have been, let's say, less than lenient in enforcing their rules, given that, Judea at the time was well known for being a problem child of a region, and so they would have come down very harsh on them. The fact that, the weapons are basically in pristine condition is another significant factor. After all, it's an area where weapons are hard to find, They're in great condition, and, well, archaeologically, they're kind of important to know about. Going from ancient history to modern and arguably future history, we have a ChatGPT and its ever-growing level of performance. Originally, it was very crude and very easily abused to create or access all sorts of things they did not want you to be able to play with. Now it's basically working at the level of a, very bad performing university student, to be blunt. But they are at a university level, which is good for students, terrible for academics, and an interesting development for ChatGPT. It's good news for, let's say, students, although if they're using ChatGPT, that nomica might be a little too generous. The advantages of ChatGPT are that they can basically use it to write their essays for them, and then ideally be able to not only be able to verify what has been written, but provide appropriate citations, improve it, and so on and so forth. But more than likely that the same students are simply going to submit what's been prepared and hope for the best, and then enjoy the, entertainment of the misconduct officer. This leads to where, universities at least don't have to stress as much, or at least until now, in that until very recently, most of these essays were fairly obviously written by ChatGPT. They were not great, and so for most students, they weren't going to pass with that as their submission, and it was less of a panic. Now, not so much, unfortunately. At least one, test of this has found that for 32 courses, ChatGPT was as good, if not better, than students for 9 of the courses. That means that we're sitting on somewhere about a quarter of all courses that are being run now, at least in this study. ChatGPT was as good, if not better, than the students who are involved, which speaks to several things, one of which is that the students are kind of shit. This is only really reinforced by the fact that as the study made the tasks more difficult, ChatGPT performed better than the students, and it wasn't much worse in terms of creativity, so it does raise issues around, what is a student gaining, or what is a student capable of that in this case, a very complicated chatbot isn't. This does raise issues though, and as is noted in the blog post, about 3/4 of students state that they intend to use ChatGPT during their studies, and unfortunately, most of the current technology used for it, and more accurately to detect it, by universities doesn't really work, anywhere between 32 and 49% of the time. The consequences of, using ChatGPT are that students who use that and don't actually learn the subject matter won't be able to apply it, which is an issue, as they'll pass, go on into the real world, and go, oh crap, how do I do my job? One relatively direct and immediate solution to this is going to be all face-to-face assessments. That is, all tests of skills, knowledge, and so on will be done directly in class, so no taking home an essay and writing it there. Rather, it would all be in-class tests, essay writing, and similar, very much like you would have had in school. In similar and the final piece of news this week, we have education in Korea, more accurately South Korea, and issues to do with, how teachers are treated. Unfortunately, a South Korean teacher has self-deleted themselves after being, emotionally, to a certain extent physically, and certainly professionally maltreated by parents, mostly because South Korea has a very different, culture to how the rest of the world would engage in some respects, or more accurately, it'd be better to say how the Western world treats teachers. In South Korea, at least to some extent, kids are sacrosanct. That is, they can practically do nothing wrong, and the law will do nothing for them. The parents strongly stand up for their children, even if the children are in the wrong. And depending on the power imbalance of what's occurred, it could very easily be swept under the rug and ignored by all involved except for victims. Except for teachers. Teachers, even if they are the victims, don't get any reprieve. And, well, this is effectively what's happened with South Korea. The teacher who self-deleted did so after a lot of abuse and pressure from parents. And this has led to, well, every other teacher in South Korea turning around at long last and going, we've had enough, you need to bring in rights and protections for us because we are done with this. Which is fair enough. And teachers already have a shit time most of the time, and especially so in South Korea, as already explained. While normally we wouldn't recommend reading articles from The Guardian, this instance may at least be one of the very rare exceptions to that, in that they do provide a fairly comprehensive explanation of some of the history, examples, and why things are the way they are, and what teachers want, given that they are quite literally walking out in protest and refusing to teach. Given that South Korea has a very competitive education environment, and particularly when you're going to university level education, this is a problem. Parents do not want their children losing out on education, and given that if that happens, the chances of them getting into the university they want to get into diminish drastically. Arguably, the only solution to this at present is basically to make Squid Game reality and see if students don't realize how good they have had it until now. That's all the news we have for you this week. Thank you for watching. If you have found it interesting, consider liking, sharing, and subscribing. Please do post any comments, questions, or suggestions you have below.